Let's talk about polar coordinates. The coordinates we're used to working with involving x and y is called the Cartesian coordinate system. It's named after René Descartes. And the great thing about a Cartesian coordinate system is that it really gives us a way to create a one-to-one correspondence between points on the plane and ordered two tuples. Our two tuples are x, y. Okay, so what I mean by that is whenever I mention the coordinate x, y, you know exactly which point in the plane I'm talking about. Vice versa. If I point to a point in the plane, you can write down what the ordered pair is that represents that point. So what we want to do now is we want to change the coordinate system we're working with, and we want to work with a new coordinate system. So now we want to describe the plane in a different way, and we're going to use the ordered two tuple r theta. Okay. So if you look at this picture on the right, you can imagine that we have a xy plane like this, except we're not going to be using x and y, we're going to be using r and theta. So there's two important reference things we need to mention. The first is that there's a polar axis, and the second is that specific point called the pole. So the pole is just the origin, 0, 0. And the polar axis is going to be the positive x-axis. Okay, so if we were to go and try to look at what the polar graph paper is, our polar graph paper doesn't look like a rectangle. Our polar graph paper kind of looks like a bunch of concentric circles with lines shooting out from the pole. All right, now these different lines are going to correspond to different angles. So let's take a second to label these. So the polar axis has angle 0, and then pi over 2 kind of corresponds to 90 degrees, and then we get a pi, and then we get 3 pi over 2 like this. Okay, if I wanted to cut the angle between 0 and pi over 2 in half, we would get pi over 4. And I could just keep adding pi over 4. So I get pi over 2 plus pi over 4 is 3 pi over 4. Then I would get pi plus pi over 4 is 5 pi over 4. Then I get 3 pi over 2 or 6 pi over 4. Then I would get 7 pi over 4 like this. And then when we come back full circle, we would get 8 pi over 4 or 2 pi. The next thing I could do is I could take this first quadrant right here, and I could divide this first quadrant into thirds. So 1/3 of pi over 2 is pi over 6. So I'm going to have a pi over 6 here. And I could just keep adding pi over 6s around my circle. So 2 pi over 6s gives you pi over 3. And then we would get pi over 2. Then we would get 4 pi over 6 or 3 pi over 2. Then we would get 5 pi over 6. 6 pi over 6 is pi. We get 7 pi over 6. 8 pi over 6 is the same thing as 4 pi over 3. And then we would get 9 pi over 6. And then 10 pi over 6 is the same thing as 5 pi over 3. And then 11 pi over 6. Okay, so these are all the points on these are all the different angles of our circle. Then we can sort of label the different radii. So you got 1, 2, 3, 4, 5 like that. And this is what our polar graph paper looks like. So why don't you guys take a moment to plot each of these points, A, B, C, and D, and we will go over these answers in class. All right, let's move on. So one of the things that we want to be able to do is we want to be able to switch between polar coordinates and Cartesian coordinates. Let's drop a perpendicular down on our picture over here and put a little right angle like this. And I want to remind you that sine of theta is equal to the opposite over the hypotenuse, and cosine of theta is equal to the adjacent over the hypotenuse, right? And in our case, the hypotenuse right here is being played by r. So really, it's like we have r for our hypotenuse and r for our hypotenuse over here. So I can actually say that the opposite side is going to be equal to r times sine of theta. And I can say that the adjacent side is equal to r times cosine of theta. So I want to label that in my diagram over here. So basically we're saying the opposite side is r sine theta. And really that's what the y value is, right? And then the adjacent side is going to be x, and that's equal to r cosine of theta. So what we've just done is we've basically just described how to switch from polar to Cartesian. And the way you do that is x is equal to r cosine theta and y is equal to r sine theta. So I'm going to highlight that because these are, the conversion equations that we were looking for in one direction. Now, what about in the opposite direction? So how do I go from Cartesian to polar? And this situation is a little bit trickier. We do not have a one-to-one correspondence between polar coordinates and the graph. And we should have seen that through example 1. Instead, what we have is a couple of equations that are going to relate Cartesian and polar coordinates. So the first equation we have corresponds to the Pythagorean theorem, and that is x squared plus y squared is equal to r squared. Okay, so we could see that by right here's x squared, here's x, here's y, here's r. This is from the Pythagorean theorem right there. Okay. The other equation that we have relating these is that if I were to take the opposite side and divide by the adjacent side, then I would have my third standard trigonometric function, which is tangent. So we're basically saying that tangent of theta is going to be equal to y over x, because tangent of theta is equal to the opposite side over the adjacent side. So I'm going to highlight that formula as well here. Okay, so that's how we're going to convert from one to the other. We'll look at these examples in class together. Let me wrap up this video by talking a little bit about polar graphs. So when we say we want to work with a polar graph, basically the graph of a polar equation is usually written like this. We usually write it as r is equal to f of theta. So what this is telling us is that theta is going to be our independent variable. And the radius r is going to depend on what theta is, okay? Sometimes you'll see books write it like this. Instead of writing it as a function, this guy looks like a function, we write it like this, f, and this is a function of two variables, r and theta, and we set that equal to 0. So there's a couple of different ways that we can describe a polar graph. And basically, the graph is the set of all points that satisfy, this equation or this equation. So in class, we'll take a look at some examples of polar graphs, and we might use some technology to help us look at those graphs. All right, everyone, take care.